Hello, and welcome to Kinetics video number 2, reading Table I. Make sure you're looking at Table I while we're doing these notes and the following problems. Table I tells us heats of reaction. And these are specific conditions. If you look at them, 101.3 kPa is pretty much normal atmospheric pressure. And 298 K is not quite what we call standard temperature because it's 0 degrees Celsius, so this is kind of more like room temperature. And heats of reaction can also just be written really as delta H. What this table tells us is the number of kilojoules absorbed or released by the process being shown. Some of these are physical dissociations, especially the ones toward the bottom. Some of them are actual chemical reactions. And we did calculate this already for potassium bromide. So again, delta H means heat of reaction. I'm going to abbreviate that a little bit. When you see delta H on this particular table, it's in kilojoules. Frequently, this is also given in kilojoules per mole. Just this particular table is only in kilojoules. Some of these are not regular 1 molar ratios. An exothermic reaction will have a negative delta H. That means energy is being released. And this will relate to what you see on potential energy diagrams. An endothermic reaction will have a positive delta H, and energy is being absorbed. You are reminded of this by the asterisk at the bottom. Very bottom, I think it says there's a minus sign, indicates an exothermic reaction. So if you're worried you're going to get that backwards, it tells you right on the table. So a couple of problems that we can do with this. We could find out if 5 moles of ammonium chloride is dissociated into ions, how much heat is released or absorbed. So you're going to go all the way down toward the bottom of the table. This is about the 5th up from the bottom. We have the dissociation of ammonium chloride. Now in this, as it's written, we're dissociating 1 mole of ammonium chloride. And when we dissociate 1 mole, the delta H is 14.78 kilojoules. Since we're looking at 5 moles, we're going to multiply this by 5. And the total amount of energy that's going to be involved. And I'm going to write the sign with this, and I'll tell you why in a minute, is 73.9 kilojoules. Now, the plus sign actually is just here to tell us that that energy is getting absorbed. So when we put ammonium chloride into water, it requires that much energy in order to be dissociated. So this would actually lower the temperature of water. Question number 2, in the formation of 1 mole of liquid water, how much heat is absorbed or released? So there's a couple of reactions that involve forming water. I'm looking specifically at the one where it forms liquid water. You're going to notice there you get a delta H value of negative 571.6 kilojoules. However, you're also going to notice you form 2 moles of water here. And we're only looking at forming 1. So we're going to take our 571.6 kilojoules and divide that by 2. So it's half the number of moles as it's written on the reference table. And this gives us negative 285.8 kilojoules. And the sign here, the negative, tells us that this is being released. So as you do this, you would actually see energy being released. It would kind of, if you will, feel hot. Another thing you need to be able to do is add a heat term to it. Oops, sorry. Is add a heat term to an equation. So find the formation of aluminum oxide. And you'll notice this is written exactly as it is. It's a little bit more than, it's a little bit closer to the top than halfway. It's probably about 10 down. This is written exactly with the same molar ratios that you see on the table. And the delta H for the first reaction up here is negative, which means energy is a product. So I'm going to write that over here. Now, some people get really bothered and they're like, hey, you can't put a positive there, it's negative. But we can't subtract things in a chemical reaction. So this negative sign right here is actually just telling us that energy is a product. If you find the formation of nitrogen dioxide, so you're just going to go down a couple. Formation of nitrogen dioxide has delta H of positive 66.4 kilojoules. That means energy is being absorbed. It's not really necessary to put the positive sign with it because you took care of showing the positive sign by showing that energy is a reactant. Finally, you do need to be able to relate these to potential energy diagrams. So you're going to find the formation of C2, H6. It's kind of right about in the middle. It's got a delta H of negative 84 kilojoules. Now, you don't have to do this exactly quantitatively. You can just sketch it out to say, okay, it's negative, which means it's exothermic. So if I start here, I always go up first. I'm going to end lower. We also need to discuss in this unit the idea of entropy, which is the degree of randomness or disorder in a system. And there's something called the law of disorder that says systems in nature tend toward disorder. Sorry, that should kind of say toward, I think. Toward disorder or chaos. So you can think about this like if you were driving out on the road and there were no rules or laws, people would drive all over the place, there'd be tons of car accidents. You can think of your backpack, if you just throw everything in there and you never organize it, it will get very disordered and chaotic. The law of disorder has to do with chemical reactions, is things in nature and chemical systems as well want to become more random. So becoming random is something we call a driving force. So here's a great example. Forming a gas. So some reactions actually occur because they form a gas, and that's a very energetically or kind of entropically favorable thing to do. So what you actually need to know to apply to questions is that systems in nature will tend toward giving away their energy, or being exothermic, and getting more random, or increasing their entropy. So when you think about why a reaction happens, it's very often a balance of these two forces, even physical systems. So if you think about putting salt into water, it wants to dissolve and become more random. If you think about putting a hot cup of coffee out on a table, it wants to give away its energy and kind of become more in equilibrium with the surroundings. So systems in nature tend to go to lower energy, but increasing entropy or randomness.